Hi, so this is the video for the R-Help session that took place on September 21st. I think most of the students got the topics that we covered, as I've seen most of you use it in your homeworks, but I still wanted to make this video for the R-Help session because maybe some of you that didn't attend, or maybe later on you'll want to go back and check these things. So I will go over the markdown document that I have for the R-Help session. And the first thing that I said during the R-Help session, which is very important in R Markdown, now I think most of you got this, but you have to define your code chunk in this way, or you won't be able to execute the code, to run the code that's in your code chunk. Or you can insert a new code chunk by going to insert right here and then clicking on R, and it will automatically give you the syntax, and you can type your code here. Okay, so that's the first thing that I mentioned in the R-Help session, and then the next part we will import some data set. Now we have to go to the downloads folder because that's where I have my dataset, and we can run the code to import the dataset. So I have the dataset saved as a CSV file, and as all of you know, this is how we import it, and we can see it here. Now after importing the dataset, it's very important to rename the columns, because sometimes you have to type in the name of the column when you do, for example, the lm command, because if you reference the column using the $sign, then that might give you errors if you're trying to, let's say, calculate the confidence interval. So how you rename columns inside a dataset that you already imported. So as you can see, I named my dataset raw data. You use the call names function, so call is in columns, and then in parentheses you put the name of your dataset equals to, or the arrow, the backward arrow, and then C, you make a vector of the names of the columns in order as they're shown in your dataset. So first in my dataset is capacity, and then second is price. So that's how I named my columns. And then you execute that command, and once we do that, we can see when we print the dataset, now it has these column names instead of the previous ones, which were a little bit more complicated to type out. Now, the best way that you want to define a linear model in R is the one shown here, which is basically you use the lm command such as you did so far. So in the way that you did so far, and then inside the parentheses you put your y variable and then the tilde sign, and then you put your x variable, or now for the newer homeworks, multiple regression, you do plus the names of the other variables, or the names of the columns inside your data set that you want to be your x variables. So then you put the comma, and then you define your data set. So data equals to, and then the name of your data set. In my case, that's raw data. So this is the way in which you always want to define a linear model, whether it's a linear regression or a multiple regression. And then summary of the model. So just to go over this again, as I said in the R-Help session, the summary gives you first the residuals. So for each value of y, it gives you the difference between the predicted and the observed y value, and then it gives you the coefficients. In here you have the estimate of each, so the intercept and the slope, and then you have the standard error for both. Then the t-value, which is equal to the t-statistic, is given here. So keep that in mind in homeworks. The t-value is equal to the t-statistic. And then here is the p-value. So also keep that in mind, that this is the p-value, the last value here. And then you have the residual standard error, and then the number of degrees of freedom, multiple r squared and adjusted r squared. So the difference between, usually we always take multiple r squared in homeworks, and we have these two different ones because as you keep increasing the number of independent variables, the r squared will inevitably grow, and this reflects the r square, the normal r square. But then the adjusted r squared takes into account actually the number of variables as well. So normally you would use the multiple r squared in your homework assignments. And then you have the f statistic on 1 and 5 degrees of freedom, and then your p-value here. So that's for the summary. Now for the now be careful here. So the f statistic and the p-value, and this is the t statistic up here. Just keep that in mind. So predicting a single value is just done by using the predict.lm function. So you do predict.lm, and then in parentheses you put first the name of your model, in my case it's mod 1, then you put comma, and then you can do it in two ways. So you can either use data.frame, and then in parentheses you put the name of the column or the variable equals to the value of x for which you want to get the predicted y value. Or the second way is to use list, and then in parentheses you put the same thing. So we see that if we run this, we get the same value twice, because these two ways are equivalent. Now to get a prediction interval, you have a small definition here, like a small explanation for what a prediction interval is and what it relates to. You also use the predict.lm, and you use it in exactly the same way, but in the end, in the parentheses, you add a comma and then interval equals to prediction to tell R that you want a prediction interval. And there's your result, again, in two different ways using data.frame and list, and you get the same numbers. And in here you have the fit, which is basically the estimate from above. So this is kind of the estimate. And then here you have the lower and the upper bound for the interval, for the prediction interval. Now the significance level, you can specify it in the following way. So level equals to 0.95. So now if we run this, we can see we get the same numbers, and that's because the default significance level in confidence or in prediction is 95%. However, if we do, let's say, 80, we will get different values. So that's how you specify the significance levels if it's something other than 95%. Now, confidence level is actually very, very similar to a prediction interval. The only difference is you put confidence instead of prediction at the very end inside the parentheses in the command. And we can see the two ways are again equivalent that we showed before. Now, when calculating the confidence interval for the slope estimate, it's not possible to use these commands, so you have to use the formula that was shown in class. And this formula basically is that to the estimate of the slope, you have to add the t-critical value times the standard error of the slope. So the standard error is given right here. So in our case, this is the slope. This line corresponds to the slope, and this is the standard error of the slope. So that's already given, and the estimate of the slope is already given in your summary. So the only thing that you need to find is the t-critical value. The t-critical value basically comes from the t-distribution, and we basically, the t-distribution is very similar to the standard normal distribution, but it's usually used for a significantly fewer number of samples. And the t-critical value takes two arguments. Actually, we need two pieces of information to calculate the t-critical value. We need the confidence, so the confidence level and the number of degrees of freedom. Now, in R, you can calculate the t-critical value, or you can use a t-table, t-standard table, and I'm going to show you how to calculate the t-critical value in R. So given a confidence level, in this case 0.95 or 95%, you calculate your alpha value, which is 1 minus the confidence level. And then in the critical value you calculate it in the following way, using the command qt, and then inside parentheses, this alpha that we expressed here, we divide it by 2, and then we put a comma, and then degrees of freedom equals to the number of degrees of freedom, which is also given, as I mentioned before, in your summary output right here after the residual standard error. So that's how you calculate your critical value using R, and we can see it here, right here. It's minus 2.57. Now, because the critical value can be minus or plus, positive or negative, you take the absolute value, and that value you multiply to the standard error of the slope, and that product you add and subtract to get the upper and the lower bound, respectively, of the confidence interval. Now, for working with residuals, most of you probably know this, but just in case you want to review and come back to this video, how you get residuals in R is by using the residuals or just resid command, and in parentheses you put the name of your model and you save it in a variable, like shown here. And when we run that code, we can see the residuals. Now, there are different plots of residuals that you can use usually to check whether the assumptions for linear regression or multiple regression are satisfied. So some of the plots of residuals that I want to show you guys is the normal plot of residuals with respect to the x or the y variable. Now, usually this doesn't matter, so you can also put just a plot of the residuals, and you will get a very similar graph. So that doesn't matter if you plot it against x or y. You are only interested if there's an outlier. Here, obviously, there's an outlier, and if there's an equal spread of the residuals above, like an equal spread of positive and negative residuals, so around the line 0. Now, the second plot is just a histogram plot, and this is used to check the normal condition, whether the data is normal. So the residuals need to, when plotted on a histogram, need to look approximately like a normal distribution. Now, this is obviously not the case here. And then the normal distribution of the residuals needs to look like a straight line, which also is not the case here.